So hello everyone and welcome back to Simcyp technical webinar series. My name is Champagne. I'm part of the translational DMPK group at Simcyp. I will host the session today. So today's topic focuses on the Simcyp in vitro data analysis SIVA toolkit. Before we start talk, I'd like to kindly request that everyone stays muted during the presentation. Should you have any questions, feel free to raise your hand or post your queries in the chat box. We have a dedicated Q&A segment at the end where we will address them. We are recording the presentation, which will be available on YouTube shortly. Next slide, please. It's my pleasure to introduce today's speaker, Dr. Ali Nimarati. Ali is a research scientist at absorption team in Simcyp. He has been working on the SIVA biopharmaceutics modules in the past few years and is leading the development of the SIVA version 5. I'm glad to have him with us today to introduce the SIVA toolkit for the biopharmaceutics and giving the example about the Itraconazole Cyclodextrin case study. So without further ado, I will hand over to Ali. Ali, the floor is yours.
Hello, can you hear me now?
Yes.
Yeah, hi everyone, this is Ali. I'm glad that I have the chance to actually explain the cyclodextrin binding constant modeling, the case study of Itraconazole to you in this session. So I have only one slide actually to introduce SIVA, and then I move to actual SIVA software to demonstrate the software from and how we develop the model from scratch. So basically, the recent version of SIVA that was released last year in August is SIVA version 5. SIVA is actually a statistical software. It has a core, statistical core with a very powerful, basically parameter estimation tool. It has several modules, starting from module 1, permeability and transport module. Different models are available, 2-compartment cellular uptake model, 3 or 5 compartmental permeability model, and the MECP model also is available in this module. In the other modules, we have enzyme inhibitions for mechanistic time-dependent inhibitors models. But the one that I'm basically focusing today is the pharmaceutics module. And basically, majority of the new features that was added to SIVA 5 is in this module. So I'm going to take you through the in vitro solubility models today for the case study. And then if we have time, I can briefly demonstrate the other basically models for these solutions. So basically, the aim of using SIVA is basically we have two philosophy of informing our PBPK models. One philosophy is that when we want to inform our PBPK model, we directly basically input the in vitro data to our in vivo software, for example, Simcyp, and then this here in this case, you have a big assumption. The assumption is that the in vitro systems exactly represent the in vivo system, which in majority of the cases not case studies it is not the case. So basically what we have, there are several parameters, system parameters in vivo that are different from in vivo system parameters. So what we are trying to do using SIVA is to deconvolute the compound parameter with the system parameters, in vitro system parameters. So either by modeling or estimation of like a specific API parameter, then we can basically move or inform our PBPK model using those estimated parameters or model parameters to inform our PBPK model. So in this case study today, I'm focusing on the parameterization of the solubility equation in Simcyp using the in vitro experiment. So I stop sharing my slide here and move to SIVA. Okay, I hope you can see the SIVA now. When you open SIVA, you can see this software, and then you want to actually select a particular model. So if you click on this one, this tab here, the drop down, you can go to a particular model that you want. Before I forget, the SIVA is covered in several focus workshops, basically for different case studies. So if you are interested in a particular case study or a particular model, and then please be in touch with our CRM team, and they advise you which basically focus workshop you can attend to which is covering the model or the module of interest. So in this one, I'm going to select the solubility, which is part of the module 2. When you select this one, you can see the screen is divided into a few different basically segments. Down here, you can see the total solubility equation in which is similar between SIVA and Simcyp. So the total solubility in Simcyp or SIVA basically is broken into its components. So the first term here is not is the intrinsic solubility or unbound and unionized solubility of the compound. The scalar here is used only if you have a particular media that is impacting on the intrinsic solubility. If this is not the case, we typically keep this one as 1, and then we basically don't scale the intrinsic solubility. The two long terms here in these two parentheses are basically representing the surfactant enhancement solubility, enhancement of the solubility due to the micellization. This is the concentration of the surfactant, and these are the binding, the partition coefficients of the API to basically surfactants. So this is for the unionized species, and then this is for the partitioning of the ionized species to the basically Micellar. The SI is the solubility enhancement due to the ionization. So for depending on the compound type, you may have a monoprotic, diprotic base or acids or amphiolites. So the intrinsic solubility is coming from these equations that are here written here. This is basically the Henderson-Hasselbalch equation. If you have a ionizable compound, again, the SI is calculated based on the intrinsic solubility, the pKa of the compound, and the pH of the media. So in the case study for Itraconazole, we have a monoprotic base, and the pK are so the first equation here shown here is used to calculate the ionizable solubility. The last term here is the solubility enhancement due to the binding of the API to the excipient. Again, in this case study, we have cyclodextrin as an excipient. So I'll show you how to parameterize the whole solubility equation using a stepwise approach. So what we have to do, I'll quickly show you the tabs here and how we can input our parameters, but then I'll also run the simulations and show you how we proceed with this stepwise approach. So in the second tab here, this is where you can apply the physicochemical properties of the compound and the compound type, and then also the intrinsic solubility. So the solubility limited, the salt limited solubility factors are shown here, and these are the partition coefficients. So what I would do, I start with the basically the first parameterization of this equation, basically based on the solubility factor. So in fact, monoprotic bases are quite ionizable in the lower pH values. So I have prepared an Excel file here that I have taken these solubility measurements from different literature. So I would basically show you how to start with the first part, which is estimation of the solubility factor. Solubility factor is basically the ratio between the highest observed solubility, ionized solubility, divided by the intrinsic solubility. So Henderson-Hasselbalch equation doesn't actually cap the value for the lower pH value, but in fact, when the compound is majority of the compound is ionized, there wouldn't be any further enhancement in the solubility because of the ionization. So in SIVA, you can easily copy paste the basically the data as long as basically the columns are I'll show you. So I copy paste this part of these are the solubility measurements in different pH values in a non-micellar media. So the surfactant concentration is 0. So I copy paste this one and then go back to SIVA. You can go to basically experimental details. So for the sake of time, I have added the I have prepared a workspace, SIVA workspace, which is filled with the physical chemical properties, so that we save time. So this is the molecular weight of and log P pKa of the Itraconazole. So it's a free form, so I select the free form, and the intrinsic solubility of Itraconazole is reported to be very, very low. It's about like 1 nanogram per milliliter. So I have added this one here. And what I want to do, I want to actually estimate the solubility factor. As I said, this is the ratio between the highest observed solubility divided by the intrinsic solubility. So I go to the experimental details, and in this empty box here, I right click here and then paste the data that I took from the basically my Excel sheet. So so you can see in this table, the media name is here, and the pH values, the surfactant concentrations, and the critical micellar concentrations are represented here. Obviously, this is a free form, so I'm not worried about the common basically or counter ion concentrations here in these two columns. And the measured experimental values are here. The standard deviation of the experimental measurements are also shown here. So if I want to actually select this solubility factor for parameter estimation, I go to the box, open this log, and then I'll go to the box, right click on this one, and select a parameter for parameter estimation. So once this is selected, now I can actually, I have already added the experimental results here, and then I go to the parameter to be estimated. So sometimes you can go with the defaults for this parameter estimation tool for the initial lower and upper bounds. But sometimes you, if you go with the default, you don't get a good basically fit. So you can play with these lower or upper bound or the initial bound, because at the end of the day, SIVA is using a minimization method to minimize the objective function. Sometimes basically it will trap into a local minima for estimation, and it doesn't give you a good estimation. So this is how you can actually basically change the area of the for the minimization function. So in this case, I select this using these default values. I can go to the run option. Here are different methods of minimization. We have a generic algorithm, hook, jeeves, or hybrid or Neldemead method of minimization. So I actually select the Neldemead. And then I select a 100 iteration for termination criteria. If in case you want to actually have a weighted estimation, then parameter estimation, then you can select a different basically option here. I don't want to actually weight these parameter estimations, so I use a equally weighted. So now I'm ready to actually run the simulation. It's very, very quick. So you just need to press this start, fitting, the green arrow here, and then it gives you quickly the estimated solubility factor. So the observed measurement versus predictions are shown in this basically graph here. I'll talk about the output later because we have added a significant output section in SIVA 5 for the pharmaceutics module as well. I'll discuss that later. But as you can see, it is not perfect for the fitting, but it is not too bad either. If I go to the experimental details as well, you can see for lower pH values, majority of the compound is ionized. This is the percentage ionization. And for the higher pH values, obviously because of this is monoprotic base and the pK1 is 4.28 for a couple of units higher pH values, and the compound is almost unionized. So now, if you go back to the parameter estimation, if you're happy with this basically estimated value, you can accept. And the if I go here, the value is overwritten here. So now this is we are done with the first stage of the estimation for solubility factor. Again, for the sake of time, for the next part, I open a new one, new workspace. So in this workspace, in the next step, I want to actually parameterize the Micellar partition coefficients, basically these KMWs for unionized and ionized species. So in the new workspace, I haven't changed anything. I just keep the compound properties the same. I just changed this solubility factor. And now I can add the biorelevant solubility measurement from my Excel sheet. So again, I copy paste this part of my Excel sheet, go back to SIVA, and then go to the experimental details, and then I paste these values by right-clicking here. So here I have some different measurements for FASIV from different labs for different pH values and different concentration of the surfactant. So again, if you look at this graph, currently this is not very good because I am using the user input partition coefficients, and these two values are 1. So we have a predicted value of log KMWs as well, which is coming from the log P. If I select this one, so as you can see, the results are improved a bit, but it's still not ideal. So what I can do, I can estimate these two parameters based on the using the SIVA, based on the experimental results. So I right-click here, use these two parameters for parameter estimation. And now, if you go to the parameter to be estimated, you can see these two parameters are here. I keep these lower, again, default value for lower, upper, and initial values for my parameters, and then I click run. So as you can see, again, obviously it's not ideal, but still I can see the using these estimated values of log KMWs here. I got a better basically predictions. So one thing here is that I'm using like a few number of basically measured values to estimate two parameters using one equation. So generally we have identifiability issues here. But there is a rule of thumb that typically the log KMWs for ionized species for monoprotic bases is 1 unit less than the estimated value. So I could have only basically estimated this neutral species and then use 1 unit less for the log KMW for ionized species. But anyway, so I accept these values here. Now, if I go back here, I can show you that these are basically overwritten here. So the next step is to basically go into the excipient model, because I wanted at the end of the day estimate the binding constants of the itraconazole to cyclodextrin. So what I can do here, I can go to the excipient model. I'll show you before I do the estimation. You can, if you click on the excipient tab here, you can select this model, reversible excipient model, and then the overall equations of the model are written here, down here, for itraconazole. Again, I have created a separate workspace for basically itraconazole, and what I have done again here, nothing is changed in terms of the compound properties. The solubility factor from the first stage is here. The partition coefficients that I estimated in the previous step is added here. I'm going to change this one to 1 unit less than the basically neutral species for monoprotic base. And so itraconazole is basically in the literature, there are some evidences that itraconazole is binding to cyclodextrin and then forming a stoichiometry of 1 to 2 or even 1 to 3. In our model, we only have 1 to 2. So basically, you can select the 1 to 2 binding constant here as well, and let's say the molecular weight of the cyclodextrin is if I remember correctly, it was 1,545. If I don't make a mistake, I forgot to actually check this one. So basically, let's say this is the molecular weight of the itraconazole. Sorry, cyclodextrin, the excipient. And then I want to actually use the 1 to 2 binding constant and also 1 to 1 binding constant, and then parameterize the binding constant for API to excipient binding. So what? Okay, so I have sets of data for itraconazole to cyclodextrin. In that the solubility is measured in various concentrations of excipient. So from 25 or almost about 25 milligram per milliliter concentration of the excipient up to around 400 milligram per milliliter. So these measurements are done in the lab in various pH values, in pH 2, pH 7, and pH 4. So what I would do in the first step, well, I can add all these values and then simultaneously estimate the 4 binding constant that I showed you in SIVA here, the 4 of them together. But an alternative approach is that because I know it's itraconazole is a monoprotic base, and in the pH of around 7, it is almost unionized. So what I can do, I can only use this set of data for pH of 7 and copy paste them here into the experimental details. And as you can see, for basically a pH of 7, itraconazole is the percentage ionized of the compound is negligible. So in that case, this is the concentration of, by the way, this is the concentration of excipients for my in vitro experiments. So in that case, I'm not worried about the binding constant of the ionized species of itraconazole to excipient, because it is almost unionized. So what I do, I only select these two parameters for estimation. So here in this graph, you can see currently with these binding constant, these two binding constant, the predictions and the experimental results are quite different from each other. But what I would do, I use the parameter estimation tool, and I change these to 1 because I don't really want to trap around 0 values. So I run the simulation. And then, as you can see quickly, it gives me the estimated values for basically K11 and K12. And the results are not too bad, much better than before. Please bear in mind that itraconazole solution formulation is dosed typically with 8 grams of cyclodextrin. So the concentration of cyclodextrin in vivo in the lumen is quite high. So that means that I shouldn't be too much worried about where the concentration of the cyclodextrin is low, and then where it is the concentration of the cyclodextrin is higher, my predictions is far better. So if you're happy with these two estimated values, you can accept these two values, and then it will be overwritten here. Next step is to actually use the measurements of the solubility measurements in the pH 2, because in pH 2, again, because the pK of itraconazole is about 4.3, so in around pH 2, a majority of the compound is ionized. So in that case, I can estimate the ionized partition coefficient. So I copy paste this part now only, and then I go back to the experimental results. I can deselect these values and then paste those new values, but I'd rather, to this case, delete now these experimental results and then paste the new ones. Okay. Let me show you here. So in this case, pH is 2. Now you can see, if you check the percentage ionized of the itraconazole is more than around 99.5% of the itraconazole is ionized here. So it is rational that I say, okay, in this case, with this set of data, I can go to the excipient data, deselect these neutral binding constants, and then only basically select these two other ionized binding constants. So again, for this case, you can see it's not very ideal between the predicted and experiment. And then if I run the simulations and then estimate the new values of the K11 and K12 for ionized species, the results are again far better, particularly where the concentration of the cyclodextrin is higher. So now I can go to the basically parameter to be estimated tab, and then I accept these values as well. So as you can see, it will change here, and then I for a third case I can verify my estimated values using the solubility measurements in the lab at the pH 4. So pH 4 is in the middle, so you can see partially it is ionized and partially not. So I copy paste this last bit where it is in pH. The measurements are done in pH 4. I deselect these two values for parameter estimation. And then I go to the experimental values again, and I delete these values for pH 2 again, and then I copy paste the one for pH 4. So pH 4, you can see the Itraconazole at pH 4 is like 65% ionized. And I'm not actually estimating any new parameter here. I'm just verifying my model. So in this tab here, you can see these are. You can also run a simulation, by the way. So with the same parameters that are used here, you can run just one simulation without fitting. And then you can see the results are, again, not too bad, particularly for the higher concentration of the cyclodextrin, which is more likely to happen in the real scenario in vivo. So it's obviously depending on the case. And the formulation of the basically the drug that you are modeling. So anyway, this is the exercise that how we use the stepwise approach to model to find the excipient binding constant. One thing that I wanted to show is this output part for the solubility, for example. If you click on this output button, you'll see a new segment, and then you can select your experiment. So in different, the experiments was basically the last one that I have added here was basically solubility measurements in different cyclodextrin concentration for pH of 4. And then you can select a different basically total solubility graph, or you can see also aqueous solubility for total ionized species or surfactant solubility. So for each of these that you select, you will see a graph down here. I show you here that there are different graphs. Obviously in the experimental in the experiment here, we didn't have any micellar. That's why this is empty in this case. And then also you have all these data here. You can copy paste these data to Excel easily and then generate the graph just in case you want to use in a particular basically paper or something. So I go back to the model. So is there any particular question?
Yes, Ali, we got some questions in the chat box. So Florent was asking which intrinsic solubility do we need to input? Is it the solubility in water?
Basically, intrinsic solubility is the unionized, free unionized solubility, or unbound unionized solubility. So solubility in water, it depends on the compound. You may get ionization, right? So you have to factor out the ionized values and then only input the unbound unionized solubility here.
There another question from Florence was the solubilization ratio predicted?
Solubilization ratio, you mean solubility factor?
Yes, sorry, solubility factor, sorry.
Yes.
Okay.
I did it in the first step, yes. This is the solubility factor. If you have a diuretic base or diuretic acid, you may have 2 solubility factor, or if you have ampholyte, you may have 3 solubility factor. So this is a monoprotic base, so I only have 1 solubility, 1 pK, so I have only 1 solubility factor.
Thank you.
Okay.
Yeah.
We have actually that one already addressed. It's about how to get access to SIVA. So SIVA is not you will need a separate lessons for that. You could contact our support team to check whether you already have that within your organization, or you want to get purchase or access to that. So you could contact our support team. I haven't seen any more questions from the chat box or anyone raise their hands. So if there are no more questions, I'd like to thank you. First, thank you, Ali, for guiding us through the SIVA toolkit for the biopharmaceutics. And we actually have more technical webinar on SIVA to come later this year. And thank you to everyone for joining us, for your attention and active participation. Should you have any additional queries later on, please do not hesitate to get in touch with us. So our next technical webinar is scheduled for the 29th of August. So in this session, Dr. Yan Yep will talk about how to use a dynamic pH-dependent DDI modeling. So this is another new module in version 23, and if you are interested in, please register through the members area. Once again, thank you for being with us today. We look forward to seeing you soon. Have a lovely day and goodbye. Thank you.
Thank you.